Hi everyone. We're going to be learning today about how to do calculations regarding the mole and do some stoichiometry. You'll be able to figure out how many atoms, for example, are in a sample of a compound, but also you'll be able to figure out how many grams of product you can get from an amount of reactant, and what's the excess reactant, what's the limiting reactant, theoretical yield, how much excess reactant is left over. So all of this involves the mole map. You'll see that I've attached two mole maps on the Google Doc. So you can find those there. Many of you will recall those from 2 years ago. Here's our first problem. Let's say that we have 0.780 grams of water. How many moles of just hydrogen atoms are in there? And then how many atoms of hydrogen are there? So we can figure out how many moles of just hydrogen there are by first finding moles of water and then finding moles of hydrogen. So you can convert from grams of water into moles of water by first getting rid of that grams of water. You can cancel that out and convert into moles of water if you know the number of grams of water per mole of water. And you'll find this on the mole map. For every 1 mole of a substance, there's the molar mass of that substance. There are 18.02 grams of water per mole of water. You can see this because on the periodic table, you've got the molar mass of hydrogen, it's 1.01. So there's 2 hydrogens, so there's 2 times 1.01. And then also the molar mass of oxygen is 16.00, so add that to 2.02, and you get the molar mass of water is 18.02 grams. So we're able to convert into moles of water, but we want to get into moles of hydrogen. So we could say for every 1 mole of water, there are a certain number of moles of hydrogen atoms. You can see it here. Every molecule of water has 2 hydrogen atoms, so every mole of water molecules has twice as many moles of hydrogen atoms. So then we can also find the number of atoms of hydrogen from that number of moles of hydrogen. You'll see this on the mole map. You can convert from moles of something into representative particles of it, whether that's atoms or molecules or formula units or ions, by multiplying by 6.02 times 10 to the 23. For every 1 mole of hydrogen, there are 6.02 times 10 to the 23 representative particles of that hydrogen. Now, specifically, that representative particle for hydrogen is atoms, because it's just H. It's not H2, it's not H2O, it's just H, simple atoms. And so you can calculate the following. All right, kind of going on to a new topic. We can kind of just take a look at what's in a box and kind of do some quick math just by kind of circling things to figure out what should result after the end of the reaction, after it's gone to completion. So let's say that we put 2 molecules of nitrogen in a box along with 3 molecules of hydrogen. What will be left over? What will be the limiting reactant, excess reactant, theoretical yield, and how much excess reactant will be left over. So in order to do any calculations about how much product you'll get, and also in order to do any of the circling, you need balanced chemical equations. So you have to put some coefficients in front to make sure there's equal numbers of atoms of each element on both sides of this yield sign. So let's take a look at nitrogen. Here there are 2 nitrogen atoms, but here there's only 1, so we need to have twice as many entire ammonia molecules to balance for nitrogen. And then there are 2 times 3, there are 6 hydrogen atoms on the right side, but there are only 2 hydrogen atoms on the left side, so you can multiply by 3, so we get 3 times 2, we get 6 hydrogen atoms on the left side. All right, so now we have a balanced chemical equation. For every 1 nitrogen molecule that reacts, there are 3 hydrogen molecules that react. And when those react together, that will yield 2 ammonia molecules. So we should have, from everything in this circle, these 2 ammonia molecules, and I left them in the circle. So what else is left? Some nitrogen didn't react. There was not enough hydrogen to react with all of it. So the limiting reactant, the thing that is all used up, is hydrogen. That determined how much product would form. If you had more hydrogen, then it would have reacted with that nitrogen. So the amount of hydrogen did determine the amount of ammonia formed. The excess reactant is the one left over. That is nitrogen in this case. Our theoretical yield is the amount of product that we can expect to get. We can expect, if all this reacts perfectly with itself, we'll get 2 ammonias. So the theoretical yield is 2 ammonia molecules. And then how much excess reactant is left over? That is determined by how much you started with and how much was used. You started with 2 N2s. Only 1 was used to react with the H2. So 2 minus 1, there's only 1 N2 molecule left over. Okay, so that's kind of a quick way of doing some simple like whole number calculations, just using these boxes. But sometimes you also have to deal with more heavy calculations. Like, for example, with that same balanced chemical equation, if you were provided 2.558 liters of nitrogen at standard temperature and pressure, so 1 atmosphere and 0 degrees Celsius, and you were also provided with 1.23 times 10 to the 24 molecules of H2, determine which one of those is the limiting reactant, N2 or H2, which one's the excess reactant, what is the theoretical yield of ammonia in grams, and determine how many molecules of the excess reactant will be left over, and finally, what would be the percent yield if only 2.01 grams of ammonia were collected. Okay, so you can determine all of those things mostly, well, most of those things, from or by starting with the amounts of each reactant and converting them into an amount of product. Here you're asked specifically to find the theoretical yield of your ammonia, your product, in grams. So we're converting into grams of ammonia in both cases. You can find the amount of grams of your products using your mole map. You can convert from the amounts of each reactant into the amounts of product. But of course, there's only one way to convert from an amount of one substance, N2, into another, NH3. And that is using the mole-mole ratio. At the center of each of those conversions is the ratio of moles of one thing versus the other. So convert your liters of nitrogen into moles of nitrogen first. Then from moles of nitrogen into moles of ammonia, and then from moles of ammonia into grams of ammonia. So in your mole map, you see that if you're at STP for a gas, there are 22.4 liters of that gas per mole of that gas. And then your mole-mole ratio, the numbers here will be the coefficients from the balanced chemical equation. For every 1 and 2, there should be 2 NH3s. All right, so for every 1 mole of N2 that reacts, you should form 2 moles of NH3. And then for every 1 mole of NH3, there's a certain number of grams of it, the mass of it, grams. And so that's the molar mass, 17.04 grams. That's from the periodic table. And you can also do a similar calculation for hydrogen. We have a certain number of molecules of hydrogen. So that's a representative unit. We need to get out of that by using 6.02 times 10 to the 23 molecules of it, or any representative unit, per mole of it. Right, so that molecules is on top and bottom, that's out. And now to get from moles of H2 into moles of NH3, we can use the balanced chemical equation, for every 3 moles of H2, there's 2 moles of NH3. And then for every 1 mole of NH3, there are 17.04 grams of NH3. Yeah, it's pretty much always going to be 1 in front of moles, except in mole-mole ratios. So we're able to calculate these two amounts of product. The smaller one will be your theoretical yield. So you can expect to get 3.89 grams of ammonia formed if all of that nitrogen reacts. That nitrogen determined that theoretical yield. So that nitrogen was your limiting reactant. It's the one connected to the theoretical yield. And then therefore the other reactant must be excess reactant. There was more of it than you needed. Having more of it didn't ultimately affect the amount of product that you got. It only affected what could have been gotten if there were more of your limiting reactant. Okay, so now we've determined limiting reactant, excess reactant, theoretical yield. Let's determine how many molecules of this excess reactant will be left over. So to do that, you want to use this equation. The amount of that excess reactant that you start with minus the amount that is used to make the theoretical yield should be the amount of that excess reactant left over. So let's determine how many molecules of H2 would have been used to make that theoretical yield. Right, so convert from your theoretical yield of the product into the amount of that excess reactant that would be used to make that. So let's ultimately convert from grams of NH3 into moles of NH3, and then from moles of NH3 into moles of H2, and then from moles of H2 into moles of N2. To get out of grams of NH3 and into moles of NH3, we need to use the number of grams of NH3 per mole of NH3. That's on the mole map. That's 17.04, the molar mass of it. So, and then to get out of moles of NH3, that needs to be on the bottom. Oh, here's our unit. Here's our mole-mole ratio. For every 3 moles of H2, there were 2 moles of NH3 formed. And then to get out of moles of H2 and into molecules of N2, H2, for every 1 mole of it, there's 6.02 times 10 to the 23 molecules of it. And so this is how many molecules of H2 would be used to make that theoretical yield. So if we start with 1.23 times 10 to the 24 molecules of H2 and only use 2.06 times 10 to the 23 molecules of H2 to form that amount of product, then that minus that leaves 1.02 times 10 to the 24 molecules of H2. That's how much is left over. And finally, to determine the percent yield if only 2.01 grams of NH3 were formed, compare how much could have been formed by how much, or with how much was actually formed. So it's like getting the percent grade on a quiz. How much did you actually get? Divide by what you could have gotten. All right, so you could have gotten about 4 points on a quiz, but you only got 2. That's about 50% yield. Thanks, everyone.